So today we'll be talking about maxima and minima in multivariable functions. So maxima and minima. So I'll give you a few graphical intuition rather than going into the detailed theory of this topic. So I'll start with a few graphical views, graphical ideas, and then we'll move forward towards the formula, towards the exact problems. Okay. So can you tell me how how we used to get the maxima and minima in one variable? Can you tell me?
So first of all, we
Derivative.
find the derivative and then we
Yes.
set
Yes,
it
sir.
to, and then we draw a sign scheme in which we see is the derivative going from positive to negative or negative to
To
positive.
positive. Yeah, that is
Then
one way. And what was used to be the second test? Can you tell me?
it's a double derivative test.
Double
Yeah.
derivative test.
If the double
Double
derivative is
derivative.
positive minima, if negative maxima.
So first of all, we used to see, we are talking about when the function is pretty much nice to us and we can differentiate it and we can, find all derivatives at every point, and then we are talking about maxima and minima, right? And can you tell me if function, something which is not differentiable, can it still have a maxima or minima? Yes, anybody?
Yes,
Yes,
sir.
sir.
Yes, sir.
Can we still have a maxima and minima?
Yes, sir.
Can you
Yes,
think
sir.
of such a function where it is not differentiable but it still have a minimum?
Sir, mod x. Mod x.
Yeah, it's very simple example, right? So we may come up with the corners, in one variable, we may come up with the corners, functions having corners, because at corners it is not differentiable, right? But it is still having minima over here, right? So that's the idea. Okay, that's the thing. So here it is minima. So first of all, don't think that the function, if function is not differentiable, then it cannot have maxima and minima. Just because maxima minima helps us in finding the the derivatives helps us in finding the maxima and minima of functions. Okay, so from here onwards, let's assume that our functions are very nice and they are differentiable. So what was the idea when you talk about the second derivative test? Okay, so that is, let's say y is equal to x square, right? And then this is, everyone knows that this is the point of minima, right? Is it okay?
Yes, sir.
Yes, sir.
Okay, so how second derivative test helps us in finding that minima? Can you tell me? So let's break into the pieces and then try to understand that how it works. Okay, so first of all, we find that dy by dx at x is equal to 0, right? And then let's say anything, I mean, like, and then d square by dx square, and that's what, sorry, first of all dy by dx, right, and d square by dx. So dy by dx at x is equal to 0, 0, right? At x is equal to 0, so it is 0, right? And this is at x is equal to 0 is positive, x is equal to 0 is point of minima. So am I right in saying this?
Yes, sir.
Yes.
But can somebody tell me that why this second derivative helps us?
So
See,
for
you've done
determine,
that part, right? Yes, tell me.
so for
It helps.
for determining whether it's minimum or maximum.
See,
Yes,
that's
sir.
true. But geometrically, can you tell me why we put the dy by dx is equal to 0? First of all,
So to get the slope of the tangent, like at that point.
to get the points where the slope of the tangent is 0, right?
Yes.
So
Yes.
Yes, sir.
so what does that mean? So let me move to the next page. Let me tell you that this is, let's say this is the graph. Okay, so precisely where should be the maxima or minima? Somewhere here, here, right? So these are actually the extreme points, right? So whether it has to be, when you say that the curve is smooth and differentiable, of course, when you reach at the bottom, so at this point, the change would be what? 0. Is it okay?
Yes.
Right. And at this point, of course, the change is 0. And at this point, the change is 0. And at this point, the change is 0. So what do you think that, the most common characteristic among these 4 points? Can you tell me?
So here the slope of the tangent is 0.
Of course, here at every point, dy by dx has to be 0. Right? At this point. Right? Am I right? Okay. But
Yes, sir.
what is the use of, let's say, second derivative? How second derivative helps us?
Sir, if it is positive, then we get to know that the slope is increasing from decreasing. In case of minima, the slope first it is decreasing, and after the point it is increasing.
So basically, it helps to tell about the a change in the dy by dx.
Okay, that's true. I mean, more precisely, I'll talk about geometrically, and then so that you can, grasp the things very easily. So that is something we call it as concavity, which is still not in the part of our syllabus. Okay, concave upward or concave downwards. Right. So what is that upward and the downward thing? So concave downward is if curve is opening its face downward or upward. That's what we think. Okay. So now can you think of this thing? Is it facing downward or upward? Is it opening its
Downward.
face downward or upward?
Downward.
Downward.
Yeah. Right. And similarly, this part is
Downward.
So
downward.
downward.
But what about this part?
Upward.
Upward.
Upward. And what about this part?
Downwards.
Downward.
Downward. Right? So I'm keeping the things very simple, and I'll conclude with these words. When your curve is concave upward, then your second derivative has to be positive. Right? That means opening its face upward. Now, let me make it more clear. Okay. So I would say that when it is concave upwards, that means curve is opening its face upwards. And in that case, second derivative is greater than 0. And concave downward means what? Curve is opening its face downwards. Right? In that case, your second derivative has to be negative. So what do you think that at the point of maxima, should the curve opening its face upward or downward?
Downward.
Downward.
Yes.
Downward.
Yes, downwards, right? So that's why when it is opening its face downwards, then it is the point of maxima, as you see the green parts of the curve, right? So it has to be a point of maxima. Is it okay? Right? And at the point of minima, should it opening its face upward direction or down direction?
Upward.
Upwards.
Yes. So that's why you see at this point, it is opening its face towards the, upward direction. So, of course, that is point of minima. Is it okay? Are you with me on this?
Yes, sir.
Yes, sir.
So let's move to the next part now, which we are doing. So that is multivariable function, and we know that if we are talking about z is equal to fxy, then it has to be some flat surface in the 3D, in 3 dimension. Okay, so it may be some solid or it may be some surface. So let me plot it like this. So it is a kind of surface, 3D surface, right? So can you tell me where are the point of maxima? Here and here. So can I talk about the tangent here? Anyone? Can I talk about the tangent here?
Yes, sir.
Yes, sir.
So rather than talking about the tangent here, I should talk about the tangent plane, right?
Yes, sir.
So however, we haven't done the concept of tangent plane, but I'm giving you an idea. So just like, I mean, this is just the extension. We are just transporting the ideas from 1D to 2D. So here we used to have 2D graph, and here here we have 3D graph. So here we were talking about tangent lines, and here we are talking about tangent planes, right? So can you think that at this point, if I draw a tangent either to a tangent line, that means the partial derivatives. So if I'm talking about, let's say, partial derivative in the direction of x or in the direction of y, so both has to be 0 or not?
So it should be 0.
Yes, sir.
Yeah. So first of all, if we are talking about the extreme points, so we'll say that if when we'll be using derivatives. So let's say this is the point, corresponding point in the domain. Okay. And this is the point in the, in the graph, that means A, B, and the Z value will be calculated as FAB. So are you with me on this?
Yes, sir.
So
Yes, sir.
fx at AB has to be 0 and fy at AB has to be 0. Is it fine?
Yes, sir.
Right. So these are the ideas we'll be, extending towards, when we'll move in the 2D thing. Okay. In 3D picture, in 3D graph. So let's define the things, in a more mathematical way. So first of all, I have a definition. So let f of xy be defined on a region R containing a point AB, then FAB is local maximum value of F if FAB is greater than equal to f of xy for all xy belong to an open disk centered at AB. Right. So are you getting this definition?
No, sir.
Let me explain it more properly over here. So what do you think? So this is your maxima, local maxima. Let's say this point is A dash B dash. Okay. Right.
Yes, sir.
So now if you think a small disk around this, it's a domain part, right? A small disk around it. So you take all those points and you take their z values. That means here, 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 here. Which value you think the biggest value? This is the biggest value, right?
Yes.
So of course it has to be a local maxima only when you compare it with the certain values and you get this value to be the maximum, right?
Yes,
So
sir.
at A dash B dash, you will have a local maxima if your f of A dash B dash, that means these heights are bigger than other heights, and other heights are what here? So let me draw the other heights with a different color. Let's say this orange one. So these orange lines are actually smaller, right, than the green line. True?
Yes,
Height
sir.
wise. right? So that's why we call it as maximum, right?
Yes, sir.
Yes, sir.
So the same thing I put in the wording. What I'm saying is FAB is a local maximum value of f if your FAB has to be greater than f of xy for all xy belonging to an open disk centered at the AB. Are you getting this?
Yes, sir.
Sir, how small is the disk?
Yeah. What is your question? I couldn't get it.
Sir, how small is the area around the point?
Any small, I mean, it may be pretty much small. We don't care about this. See, my only point is, so you talk about in the one variable, right? So this is your local maxima, right? But if you take a bigger interval around this, let's say this, then this is not the biggest value, right?
Yes, sir.
This is not the biggest value. This is the biggest value, right? Okay.
Excuse me, sir.
Sir,
Are you
talking
getting
about the
this?
local maxima here.
Yes. See, but this is local maximum. Why? Because you get a small interval around this point, so that if you map every value and compare the values, you find that this value is biggest. Okay, so that's why we call it as local maximum. True?
Yes, sir.
Are you with me on this?
Sir,
Yes, sir.
in definition you have defined local maximum value of f. उससे तो सर यही मीनिंग कन्वे हो रहा है ना कि f की जो फंक्शन की जो वैल्यू है वो मैक्सिमम जब होगी उसको जब हम कंपेयर करते हैं एंड इधर आप कह रहे हो कि जो हमारे जो पॉइंट्स हैं उसके अंदर कौन सा ग्रेटर है कौन सा
See, मैं
मैक्सिमम है
पॉइंट को
उस
ग्रेटर नहीं
पर्टिकुलर
कह रहा हूं, मैं कह रहा हूं पॉइंट ग्रेटर लेस नहीं है. मैं ये बोल रहा हूं कि at x is equal to a, your f of a is bigger than any other value f of x which are over here. I'm talking about the heights, not about the domain, right? So when I'm talking about the values, so I'm talking about the height,
ओके सर
right?
ओके
Are you with me on this? Are you getting this?
यस सर
Okay. So are you with me on this?
Yes, sir.
So how you write the definition of local minima? F of AB is local minimum value of f if what should happen? F of AB should be
less than or equal to.
yes.
F of xy.
Yes. For all xy belongs to an open disk centered at A. Is it right?
Yes, sir.
So, are you fine with this local minima
Excuse me,
definition?
sir. Sir means
Yes.
लोकल मैक्सिमा में जो ए और बी पॉइंट्स हैं उन पर वैल्यू मैक्सिमम है या फिर वो पॉइंट्स बड़े हैं.
वैल्यू मैक्सिमम एग्जैक्ट नहीं, मैं ऐसा बोल रहा हूं, ध्यान से समझो. ए बी कभी भी बड़ा या छोटा नहीं हो सकता है. ए बी क्या है? पॉइंट ऑफ मैक्सिमा, राइट? और ये हाइट क्या है? मैक्सिमम वैल्यू. ठीक है. तो व्हेन आई से दिस एफ ए बी, दिस इज अ जी वैल्यू, राइट? And when I talk about only AB, this is point of maxima or maybe minimum. Is it okay now?
सर डेफिनेशन के अंदर हम मैक्सिमम वैल्यू की बात कर रहे हैं ना मतलब फंक्शन की वैल्यू की बात कर रहे हैं ना.
हाँ हाँ, फंक्शन की वैल्यू की बात कर रहे हैं.
Okay.
और AB को क्या बोल रहे हैं? पॉइंट ऑफ मैक्सिमा.
Yes, sir.
Right? And I'll write it as AB is point of maxima. That means the point where we achieve this value. And here AB is point of minimum. Is it okay? Now tell me, is it okay?
Yes, sir.
Yes, sir.
So we have a new definition over here, and that's what? An interior point of domain of f of xy where fx and fy both are 0 or both or 1, it may be 1, both fx fy do not exist, यानी क्या हो गए, कॉर्नर पॉइंट हो गए एक तरह से, ठीक है, is said to be a critical point. True? Are you getting this?
Yes,
ठीक है
sir.
भाई, बोलो. Is it okay?
Yes, sir.
Okay, so now there is an interesting point which we talk about, that is, we call it as a saddle point. A differentiable function f of xy has a saddle point at critical point AB if in every open disk centered at AB there are points from domain such that f of xy is greater than f of AB and f of xy is less than f of AB. Right? Is it okay? ये saddle point क्या है? Before talking to the saddle point, have you ever heard about point of inflection?
Yes,
किसी ने
sir.
पढ़ा है?
Yes,
Yes,
sir.
sir.
Yes, sir.
What is that point of inflection? Can you tell me?
So where the f double dash is equal to 0.
Yes, sir.
Yes,
So,
sir.
so double dash zero होने का मतलब क्या? Can you give me some example on that?
So basically, if we draw the slope of tangent, that slope also turns out to be, parallel to the,
So can you
tangent.
give me some example?
X cube.
The
Yes.
2x.
X cube.
2x.
Simplest,
X cube. X cube.
simplest example. Okay. So something like that. And why is it so? Why it is so? Can you tell me why it is a point of, either it's not the point of maxima, not the point of minima. Can you tell me why? Anyone?
At 0 positive, it's increasing, and at 0 negative, it's decreasing.
Yeah. So eventually what happens? Let's see. So let's compare it with another example. Let's say f of x is equal to x square. Okay. Oh. Let me make it another way. Now. So is it okay?
Yes.
Yes, sir.
Now this is 0, 0 is a point of minima. Why is 0, 0 a point of minima? See, you pick any interval around 0, 0. This is one interval. Let me pick it another interval, or let me pick even, let's say, smaller interval. Let's say this and this. Now, can you tell me if I take the values from one by one, right? Let's say I take the values from red interval, bigger interval. So what do you think? All the values are what? Bigger than f of 0?
Yes, sir.
So what is your f0? It is 0, right? But if you take f1, it is 1. If you take f2, it is 4. If you take f minus 2, it is again 4. So all those values, this 1, 4, 4 are greater than 0, right? Are you with me on this?
Yes, sir.
Yes. So now if you take values from even green interval, let's say very much close to 0, even then those values are what? Greater than 0. Right?
Yes, sir.
Even if you take heights, if you select points from domain and you take heights on in pink interval, even those values, let's say these heights are greater than what? 0. True.
Yes, sir.
So, but this is not happening with this case. Why is it so? So let's say you pick a larger interval, right? And this is your value. And this value is what? 0. At x is equal to 0, f of 0 is what? 0. Are you with me on this?
Yes, sir.
Yes, sir.
So now what happens? So if you take values around x is equal to 0, there are values which are greater than 0 and there are values which are lesser than 0. Right? So no matters which interval you choose, you'll always get values greater than 0 and less than 0, right? Because f of 0 is 0 to us. That's why we are comparing with f of 0. So if you take green interval as well, so there are also points again which are greater than 0 as well as less than 0. Even if you make the interval smaller, let's say you make the interval, you take a shorter interval to that, every time you will get values which are bigger than 0 as well as smaller than 0. So here 0 cannot be the point of maxima or 0 cannot be the point of minima. In fact, we should call the 0 as a point of inflection, a point of change, rather than saying that it is a point of maxima or minima. So 0 is not your point of maxima and not minima. Why? Because you are getting few values here which are bigger than this height, and you are getting few values here which are smaller than this height. And this happens every time, no matter which kind of interval you choose. Okay, so that's why it becomes what? Tell me, it becomes what? Point of inflection, right? Is it okay? So
Yes.
similarly, corresponding to the point of inflection, we'll be having point of saddle point over here. So this is just a kind of graphical interpretation of that how we how we evaluate the things. So let me tell you about the working rule. Second derivative test for local maxima, minima, or maybe a saddle point. So more precisely, I would call it as extreme values. It can be a saddle point, it can be a maxima, it can be a minima, or maybe an indecisive state. Okay, so we start with this. So let f of xy, right, and its first and second order partial derivatives are continuous throughout an open disk centered at AB, and first necessary condition is satisfied, that is partial derivative of x at a partial derivative of f with respect to x at AB is 0 and partial derivative of y at AB is equal to 0. So now these things will happen, right? So first of all, f of xy has local maxima at AB if this thing happen. What is that thing? Fxx should be negative and fxx times fyy minus fxy whole square should be greater than 0. So you will have a point of maxima if these two things happen. What are they? Second partial derivative with respect to x should be less than 0 and this expression should be greater than 0. Okay. Secondly, what? fxy has local minima at a if these conditions are true. And what are they? Fxx has to be positive and fxx fyy minus fxy whole square should be positive at AB. So I'll mark it as this is your local minima if this thing should be positive and this will still remain positive. So in both the condition, this expression needs to be positive. Okay, and we'll have a saddle point if this thing happens. Fxy has saddle point at AB if this expression, if you find this expression and this expression is negative, then you call this as a saddle point at AB. And what is our fourth condition? Fourth condition is simple. We'll say that if your fx x fyy minus fxy whole square is equal to 0, then you say that you simply call it as at AB. Then you simply say that test is inconclusive. You cannot say anything about that point. So your test is inconclusive. Okay? Are you getting this? Are you getting this point?
Yes, sir.
Sir, switch to the previous page, please. Done, sir.
Okay. So now let me break the things. We call it as this as saddle point. Change the color a bit. Yes. So this is saddle point if this thing happens. So now can anybody infer that why I am putting this thing? Why I'm putting this thing that f of x is greater than 0 and here I'm putting f of x is less than 0. Can anybody tell me? fxx की क्या importance है? Can anybody tell me? Can anybody tell me what is the importance of fxx? Yes. Somebody can tell me what is the importance of fxx?
So we are checking
Double
the
derivative.
double derivative in a particular direction.
तो डबल डेरिवेटिव नहीं दैट इज फाइन बट वो जो डबल डेरिवेटिव वर्ड हम यूज कर रहे हैं हमने यहाँ पे किस लिए चेक किया था वो डबल डेरिवेटिव यस व्हाट वाज दैट
मिनिमा एंड मैक्सिमा
हाँ कनकेविटी के लिए चेक किया था ना फेस ओपनिंग के लिए चेक किया था ठीक है तो यहाँ पे अगर fxx जो है वो लेस देन 0 होगा तो एक तरह से अगर हम पार्शियल डेरिवेटिव करेंगे किसी भी ऐसे कर्व ली हमने स्लाइसिंग करी स्लाइसिंग करके जो पीस आया उसका देखेंगे कि फेस ओपनिंग कहाँ पे है उसकी फेस ओपनिंग अगर डाउनवर्ड होगी तो ऑफ कोर्स वो क्या बनना चाहिए पॉइंट ऑफ मैक्सिमा बनना चाहिए समझ आ रहा है आइडिया कि fxx क्यों कैलकुलेट कर रहे हैं आर यू गेटिंग दिस पीस
यस सर
ठीक है तो मैं ये सारी चीज नहीं समझा रहा हूँ मतलब बिल्कुल थ्योरेटिकली नहीं समझा रहा हूँ लेकिन तुम्हें कुछ आइडिया दे रहा हूँ कि fxx क्या है एक तरह से कनकेविटी है कट करके So you are slicing down your curve, right? And then you are getting the ideas about the concavity of the curve. So if it is opening downwards, then you say that I'm talking about the maxima. That's why it is negative, and that's why we are talking about the point of maxima. Okay, right? Because it is downward. True. And similarly, if your fxx is positive, what does that mean? Yes, anybody?
Sir, it's concave downwards.
Concave
Sir,
upward, not
upwards,
downward.
upwards. Yes, sir, upwards.
हाँ, तो जो it will be a kind of bowl shape. तो फिर वहां पे हमें क्या मिलना चाहिए?
Minimum.
Minimum.
Minimum मिलना चाहिए. I'm not talking about this expression. I'll talk little about this expression, not more than that. But this is the working rule. तो कल हम इसके ऊपर questions करेंगे, right? In our upcoming lecture, we will be doing 2 or 3 questions about this. कि कैसे maximum minima हम find out करेंगे, तो practical उसके सारे एस्पेक्ट निकालेंगे ये 4 रूल यूज करके. So I'll conclude my lecture by saying this, that this expression which we are calculating, right? So this is actually a form of determinant, and that determinant is fxx, fyy, and here fxy, here fxy. And this determinant is called the discriminant of f of xy. तो ये theoretically आया है, हम उसकी डिटेल में नहीं जा रहे हैं. It can be derived from actually a Taylor series of 2 variable functions, so which is not a part of our syllabus, so that's why I'm not discussing it here. So this is discriminant of f of xy, or sometimes we call it as Bayesian, and that's why this expression is sometimes denoted by h. So if I'm talking about h, so I'll be talking about this expression.
Sir, why
Right?
are you interested in calculating this h?
So can you tell me what kind of idea this product is representing? So okay, just tell me what is your fxx?
Concavity?
Yes. Now you're saying the right thing. Okay. So if your fxx is a concave upward or maybe downward, right? We don't know. After evaluating the expression, we'll come to know that. Of course, for different question, it will be different. So what is your fyy? Tell me, what is your fyy? This is again concavity, right? But in a different direction. Are you with me?
Yes, sir.
Can you listen to me?
Yes, sir. Yes, sir. Sorry, it was lagging.
Oh, okay. Sorry. Then sorry from my side also. Okay. So tell me, if I take the product of these 2 concavities, what can happen?
Sir, a new concavity.
No.
हो जाएगा.
नहीं, ऐसा कुछ नहीं है. Actually, concavity को हम measure जब करेंगे तो एक number की तरह करेंगे, ठीक है? So basically हम यहाँ कुछ और find out करने की इच्छा नहीं रख रहे हैं. Our main aim is to determine whether these 2 concavities are actually they are agreeing or they are fighting at some point. So if they are agreeing, मान लो दोनों positive हैं, तो इसका मतलब क्या होगा? तो दोनों ही अपवर्ड होंगे ना, इस डायरेक्शन से भी अपवर्ड और इस डायरेक्शन से भी अपवर्ड, ऐसा करके, राइट? समझ में आ रही मेरी बात?
यस सर.
तो देखो, मैं इससे ऐसे कहना चाहूंगा कि अगर जैसे मैंने पीछे एक एग्जांपल बनाई है, लेट मी गो टू दिस. सो इफ यू स्लाइस इवन बाय लेट्स से बाय दिस प्लेन पैरेलल टू द x axis or by parallel to the y axis, right? So in the both ways you will have a kind of concavity इस तरह से, और इसको करोगे तो इस तरह से ऐसे, तो दोनों की डाउनवर्ड आएगी कि नहीं आएगी?
यस सर.
हाँ, तो दोनों कॉन्केविटी एग्री करेंगी कि नहीं करेंगी? बोलो, सही बात है?
यस सर.
तो दोनों कॉन्केविटी एग्री करें तो हमें दोनों साइड से क्या आइडिया मिलेगा कि पॉइंट ऑफ मैक्सिमा बनने जा रहा है ना? समझ आ रही है मेरी बात?
यस सर.
और अगर दोनों कॉन्केविटी एग्री ना करें तो क्या होगा?
It may be maxima or minima.
ना, it may not, it cannot be anything actually. सी यहाँ पे क्या प्रॉब्लम हुई हमारे y इक्वल टू एक्स क्यूब के साथ, कि ये एक साइड दूसरी साइड के साथ एग्री नहीं कर रही है,
Yeah.
राइट? सो व्हेन योर एफ एक्स एक्स एफ वाई वाई आर नॉट एग्रीइंग, तो तुम्हें क्या प्रॉब्लम आ जाएगी? सैडल पॉइंट बन जाएगा वो। जैसे यहाँ पे पॉइंट ऑफ इन्फ्लेक्शन बन रहा है ना, वहां पे क्या बन जाएगा?
Saddle point.
Saddle point. ठीक है? So I'm just giving you the ideas. I'm not talking about the whole expression, right? Because whole expression contains some theoretical aspects which are not part of our syllabus. So that's why I'm not discussing those things. But I'm telling you that this expression is actually, deals with the concavity part of the curve in order to be sure that whether it is maxima or a point of minimum. Okay?
Okay, sir. Thank you.
So basically your idea was why we are calculating the fxx and why we are calculating fyy. So my answer in one line would be, so we'll be dealing with the concavity part in order to sure that whether it will be a point of maxima, point of minima, or maybe a saddle point. So that's why we are looking at the second derivative expression.
Yes,
right?
sir.
Okay?
Yes, sir.
So rather than going into the theory, I'm just telling you the idea that why we are calculating it. Okay?
Yes, sir.
ठीक है. So now, can you? So that's it for today. If